Okay, so let's continue with our introduction to the geometry of surfaces embedded in Euclidean space. We were up to what we call the second fundamental form, as we want to look at the rate of change of the normal vectors to a surface along a curve, and use that as a measure of the curvature of the surface and other characteristics of the surface as it's embedded in three-dimensional space. So we want to understand how the unit vector is a function of a parameter along a curve changes along that curve on S. So we form a quadratic form. Okay? It's a funny minus sign here. We'll see why it's there. But the quadratic form is just dn, the change of n in a little interval, dotted into that interval. We made the metric last time, and that was just the quadratic form, the symmetric quadratic form of dr dotted into itself. Okay, and that gives us a way of measuring lengths and angles within the surface. Now we're looking at how the surface is bent in the three-dimensional space. So we look at how the pin cushions of Gauss, the unit normals, change as we move around the surface. That's the idea of it, and we'll get a good intuition into this object as we go. Okay, so the claim is this measures the projection of the curvature along the curve R onto the normals. Okay, so it's a measure of the normal curvature to the surface along a particular curve which is embedded in the surface. So it has to do with normal properties, as you can imagine, seeing dn here, not the intrinsic properties of measurements that can be made directly on the surface. So let's verify this claim. So we'll just recall the curvature of a curve R of S. We take the second derivative of it with respect to arc length, okay, and then that points in a direction that's called little n hat, and the magnitude of it is called the curvature kappa of S. Kappa can carry a sign as well as a magnitude, actually. Okay, so that's what it was, and we remember it. We saw curves in Euclidean space, bent curves, and we calculated kappa in various cases and got an intuition into it. Let's see, for example, for a circle, we verified that kappa is just 1 over the radius of the circle. Small circles have a lot of curvature, big circles have less curvature. Okay, kappa carries a dimension, okay? It goes like 1 over length. As you see from this equation, on the right-hand side, we have 1 length upstairs, 2 lengths downstairs. And so kappa carries an extra dimension of length. Downstairs, it goes like 1 upon r, where r is the circle that best fits the curve at the point of interest. Okay, now to relate all this to this quadratic form, we note that n, of course, capital N, the normal to the surface, I'm always using capital N for that, is of course perpendicular to any curve in the surface itself, whose, for example, in this case, the gradients of the position of the curve lie in the tangent plane at that particular point. So n dotted into that is equal to 0. If I differentiate this with respect to S, okay, then you see what I get. I'm going to get something equals 0, and differentiating it, I'll first differentiate n, then I'll have another term differentiating r prime, and so I'll get this equality, right? So I see that n prime dotted into r prime can be written as n dotted into the second derivative of r. So I can come back to the second fundamental form and write that in there. So just write it in as a second order form, okay? Divide through by ds and multiply through by ds twice, so I can write these differences as derivatives. And then you see I have n prime dot r prime, okay? And that's minus n dot r double prime. And R double prime brings in the curvature of the curve that's embedded in the surface. So I just write that here as kappa dot little n hat. And then I see that's the projection of the curvature of the curve in the normal direction. And so that'll be called kappa sub n. That symbol might be a little bit small for you, but I've recommended to you that you follow along in supplementary lecture number 9, and then you can see this formula right there. Or if you have a computer with a big screen, you can also see it clearly. It's big enough for that. It's just not good enough for small screen devices. Okay. Okay. So that's what I wanted to show. Okay. That the second fundamental form is related to the normal component of the curvature of a curve at that point. As I change the direction of the curve, I'll get different values for the second fundamental form. As you can imagine, it depends upon the direction in which dr is changing. Okay. Now we can talk about the eigenvalues of n prime of s. We've already discussed that n prime can be thought of as a linear operator that operates on vectors in the tangent plane. Okay. And we already showed that it's self-adjoint. So it's going to have a complete set of eigenvectors, and it'll have real eigenvalues, and the eigenvectors will be perpendicular to one another. Okay. So if I choose R prime to be one of the eigen directions, okay, then minus n prime in that direction just reproduces that direction and multiplies it by the eigenvalue. That's just the definition of diagonalizing a matrix. And then similarly for the second one. Again, funny minus signs, but just bear with me. That's just the way it goes. Okay. We'll have funny minus signs here, and that'll absorb signs later, so in the long run maybe it's okay. Also then, the second fundamental form applied to unit vectors has its maximum at k1 and its minimum at k2, and those directions are perpendicular. Just remembering my linear algebra about symmetric matrices. In general, if I take a direction nu, which is a linear superposition of E1 and E2, right? So that's a completely arbitrary vector in the tangent plane, just parameterized by the two eigenvectors of n prime. Okay. If I do that, then I can evaluate the second fundamental form and get a useful relationship for kappa sub n, the normal component of the curvature at that point. So I just write that here, and then I just write down the second fundamental form. Okay, nu prime. Okay, that's the direction in which I'm headed in. So that's the dr prime ds. Okay, is nu. I'm just putting in here for r prime, okay, and then over here I'm just putting in n prime, okay. So r prime is nu in this particular situation, and n prime is evaluated in that direction. Okay, so that's what I write out here. N prime is evaluated in that direction, dotted into that direction. Okay, just coming back and writing out the second fundamental form. Now, when n prime hits this linear combination, I just use its linear character, so linear operator. So it hits the E1, reproducing it in direction, but multiplying it by the eigenvalue k1, and similarly over here. So n prime is then taken care of. I have a dot product to do. Very easy because E1 and E2 are orthonormal. So I get k1 cosine squared theta plus k2 sine squared theta. Okay, and so now I see very clearly in this particular case the angular dependence of the curvature in the normal direction. I can just relate it to the two eigenvalues of n prime, and that's very handy, and that tells me a lot about it. Okay. So the eigendirections of minus n prime are called the principal directions. Okay, and then the K1 and K2 are called the principal curvatures. Okay, K1 and K2, and we'll be looking at lots of examples where we can look at a surface and deduce what K1 and K2 are. Okay, or calculate them in some straightforward way. But let's remember that the eigendirections of n prime are called the principal directions. N prime is a linear operator. Okay, it has some properties, of course, which are independent of the basis in which you might write it, and those are the geometric quantities of interest. In particular, it has a determinant, which remember from linear algebra is independent of the basis. If you're working in a diagonal basis, then the determinant is just the product of the two eigenvalues, right? In that basis, the 2 by 2 matrix would just be K1 and K2 down the diagonal, and the determinant would be the product of them. Another invariant is the trace. If we take half the trace, okay, it'll be a half K1 plus K2. We're applying this to minus n prime here. That's the funny signs again. The determinant is called K, the Gaussian curvature, okay? And the mean curvature is called, well, it's called mean curvature. It's written as H. Okay, okay. Now, we've introduced the Gaussian curvature before. We've had lots of discussion of it and lots of intuitive visualizations of it. And we'll show later that this fundamental definition of it in terms of the properties of the surface, local properties of the surface, reproduces all of our other statements. And that'll be fun to do. Okay, at this point, here's a very new perspective on it. The Gaussian curvature is the product of the principal curvatures at that particular point. Okay, so for example, if I have a surface, then I'm going to look for a direction in which I have a maximal curvature, and perpendicular, I'll have the direction of minimal curvature, and I'll take the product. And I'll have the Gaussian curvature. And maybe that'll be a handy way of doing calculations. Okay. So far this has been relatively abstract. Let's write out everything now as 2 by 2 matrix forms. Very handy, very straightforward, and bring it down to earth. Okay. So how would I do that? Well, I'll just use a standard basis and expand all of my vector algebra in that basis. And the natural basis, of course, is just going to be R sub u and R sub v. I'll put a mesh, a UV mesh down over my surface, and then I'll have the tangent vectors to the mesh like that, and I'll just expand my quantities in that language. For example, I know that the derivative of n in the u direction is a linear combination, lies in the tangent plane, so I can find coefficients a and a for which this is true. And then similarly, n differentiated in the b direction will be another linear superposition of them. And I choose to label a11 and a21 here, anticipating that I want to get standard symbols for 2 by 2 matrices. Okay, so then I'll write n prime in general in this way. So n prime, remember, was just n sub u times u prime plus n sub v times v prime. That gave me the rate of change of the normal vector. Okay, and then so if I write it in this fashion, then I'm expanding n prime in terms of the basis for the tangent space. Okay, and then this is a standard way to then present n prime in a particular basis, okay, as a 2 by 2 matrix, because now another way of writing this is to say I now have a matrix representation for n prime. It is applied to a vector whose components are u prime and v prime, and what does it do? Well, it gives me a matrix times this vector. And I can see that this simply reproduces this formula here, because for example, just multiplying it through, I'll have in the upper component the RU direction A11 times U prime, that's here, right, plus A12 times V prime, and that's here. And then in the RV slot here, okay, the result of the application of n prime will then be what I see here, okay, it'll be on the matrix side here, A21 times U prime plus A22 times V prime, and that reproduces. So I'll just use the 2 by 2 matrix form to do my arithmetic. Okay. Now A11 and A12, I should be able to relate those quantities to others that I've already introduced, and that's what I want to do. Relate this to the fundamental forms, A11 and A12. Okay, so here's the second fundamental form. Here's dn, okay, and here's dr, and I'm just going to write it out, okay, just the way we did for the metric. Okay, exactly the same way we did for the metric, and so I'll have a term n sub u dotted into r sub u multiplied by du squared. And collecting up all the other terms like that, I'll have a quadratic form of that kind, and I'll give things handy names. The coefficient of du squared, I'll call that little e. In the case of the metric, we call it capital E. Okay, and then the cross term, I'll call that twice little f, and for the other one, I'll call that g. Okay, and I have these funny minus signs around. We'll just put up with them. Okay. And so here then I can calculate E, F, and G in terms of things that I've already discussed. In particular, I see from this formula that little e is minus n sub u dot r sub u, and I've written that down here. Oh, then I've also noted one of my equalities, as we showed before, where we started off with n prime dotted into r prime. We could write that as n dotted into u double prime. And I use the same observations to do that for these particular components. In particular here, I'm just starting with the observation that n dot r sub u is equal to 0. N is perpendicular to the tangent plane. If that's the case, then I can differentiate this fellow with respect to u, okay, and get this plus this equals 0, and then I read off this identity, okay. And I do that everywhere in sight to make things handy. Okay, I can move my differentials around, as shown there. So a little f being n sub v dot r sub u, and g being minus n sub v dot r sub v, and I can write some identities like that, and we'll keep them in mind, and we'll use them later, because those identities will clean up some of our algebra. Okay. So now my task is to relate the matrix with the aij's, a's, in terms of coefficients of the first and second fundamental forms. Okay, those are the fundamental forms. You give me a surface, I can calculate them. I want to compute now the a's in terms of them. Okay, so what do? Well, I just take my equations here and I take some dot product so that I isolate the pieces of the second fundamental form, the first fundamental form, and the coefficients A11, A21, etc. So in this first one here, I've taken the relationship before, where I had minus e is n derived with respect to u dotted into r sub u, and I've written it out in terms of e and f, right? So that's just to come back here and rewrite things in terms of the first fundamental form on the right hand side. Okay, so right, so we see it right here. Okay. So E was minus n sub u dot r sub u, and then I can write these expressions in terms of, for example, the definition of the A, so R, so N sub U, just put that in here, okay, dotted it into R sub U, you see. Oh, when I do that, then I'll get R sub U dotted into R sub U. That's capital E of the first fundamental form. I'll get R sub U dotted into R sub V. Okay, that's the other component of the metric called capital F. And I just collect up all of that stuff. So it's straightforward. And look at supplementary lecture 9 if you need to check on those details. And it's stated here. So E is this dot product, and now I just substitute in that N is equal to this linear combination. Okay, taking the dot product and identifying the components on the right-hand side that are the metric, I write it all out. And I do that for each one of those different equations, and I get 4 equations like this. Sort of looks like a mess, right? Well, you know how you clean it up. We're trying to write things in terms of 2x2 matrix forms. Here I have the components, the little a's. I've written that already as a 2x2 matrix. And so if I just look at this for a moment, I see I can write it in matrix form. On the left-hand side, I have E, G's, and F's. Okay, bring it together as a 2x2 matrix like this. On the right-hand side, I see A's dotted into the metric, and I can factor it as just the matrix representation of minus n prime, and then here the matrix representation of the metric. So you just check it. For example, let's check that this component gives me the right thing. Okay, it should be minus E is equal to A11E plus A21F. So A11E plus A21F. So it works, and just check the other ones that I've gotten my indices in the right order to do that. Okay, great. So now I can solve for n prime. Okay, I can calculate the linear operator, the rate of change of the normal as I move along a curve in terms of the first and second fundamental form. Okay, so I see that here, right? I'll just want to stick on the right-hand side the inverse of this object. I'll just call it E. I'll just call a matrix with a -1 as the inverse, right? And so if I do that, then I'll get matrix for the second fundamental form times the inverse matrix of the first fundamental form is equal to the matrix for n prime. Okay, and watch the minus signs, and there you go. You're all set. Okay, now in the lecture, I write down the actual inverse of this two-dimensional symmetric matrix. It's trivial. You know, stock formulas to write down the inverse of the matrix. If it's 2x2 and it's symmetric, it's just a simple little formula, and it's written down in there. And maybe I'll refer to it later. At the moment, I don't really need it, because what I want to do is to look at the geometric quantities hiding here in n prime. Okay, one of them is the determinant of n prime. That's the Gaussian curvature. Another one is the trace, okay, of it, and that's the mean curvature. Okay, well look, if I want to take the determinant of this fellow, that's easy. The determinant of a product of matrices is the product of the determinants. The determinant of the inverse of a matrix is 1 over the determinant of the matrix. Okay, and so I see on the right-hand side the determinant of the second fundamental form. That's EG minus F squared. And then downstairs, I'll have the determinant of the first fundamental form, and I've written that down here. And then similarly, doing the arithmetic for the mean curvature. Okay, and so I've made a lot of progress, and I'm understanding the rate of change of n prime as I move around my surface. Okay, so a lot of algebra today, and I don't want to just pass through it. I want to illustrate it and get used to it. So we're going to look at some applications now to various different kinds of interesting surfaces. Okay, we'll pose some conceptual problems as well as do some illustrations and have some fun with that. and we'll do that starting next time.